In this video, we're going to do some more examples of translating statements into symbolic logic. So for each of the following, I'd like you to write them out as English sentences and then say whether they are true or false. So take a look at all of those, pause the video, and we'll talk about them together. Our first is, for any n in the integers, there is an m in the integers such that n plus m is equal to 0. So for any n in the integers, or for any integer n, there is some integer m such that n plus m equals 0. So is that a true statement? If n is in the integers, then negative n is also in the integers. So negative n plus, or plus n plus negative n is going to be equal to 0. Great. And if n happened to be 0, the opposite of 0 is just itself. So excellent. Yes, this is a true statement. Next, there is an integer n such that for every integer m, n plus m equals 0, there is an integer n such that, so this is there is, for any or for every, for any m in the integers, n plus m equals 0. Is this a true statement? So we've got some integer n, we've got a fixed n, and is it the case that for any m, n plus m equals 0? Well, okay, let's say n plus 12 equals 0, n plus 4 equals 0. Can both of those be simultaneously true? Here that means n equals negative 12, and here that means n equals negative 4. N can't simultaneously be both of those things, so this is a false statement. There exists an integer n such that blah 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 fixes our n and means that it must be this one n for every other integer m. So written in this form, this statement is false. Observe that the statement preceding it was almost exactly the same. It just had a reversal of the order of these two phrases, but it was true. Next, for any n in the natural numbers, there is an x in the power set of n, so x is a set, such that the cardinality of x is equal to n. For any natural number n, there is a set x, and we could say in the power set of n, or we could say subset of n, because that's what it means to be in the power set of n, such that the cardinality of x is equal to n. Is that a true statement? Yes, this is true. So if we let n be an element of the natural numbers, then the set 1, 2, ... up to n is a set with n elements. The cardinality of that set is n. It has n elements in it. And that set 1, 2, ... n is in the power set of the natural numbers because it is a subset of the natural numbers. So yes, this is a true statement. Next, for all x and y in the real numbers, x greater than or equal to y implies negative x is less than or equal to negative y. For any or for all real numbers, x and y, if x is greater than or equal to y, then negative x is less than or equal to negative y. That would be one way to write that. We could also write that as an if-then statement. So if x and y are real numbers such that x is greater than or equal to y, then negative x is less than or equal to negative y. And is that a true statement? Yes, if we multiply both sides by -1, then that reverses our inequality. So yes, this is true. And lastly, for this section, x and y being natural numbers implies that x minus y is in the natural numbers. Again, we could write that in different ways. We could either write it as an if-then statement or as a universally quantified statement. So we could write it as, for any natural numbers x and y, x minus y is a natural number. So we could write it in that form. We could also write it as if x and y are natural numbers, then x minus y is a natural number. So we could write it in either of those forms. Now, is this a true statement? This is going to be false. So, for example, if x is 3 and y is 5, then x and y are in the natural numbers, but it's the case that x minus y is -2, which is in the integers, but it is not in the set of natural numbers. Next, we're going to go in the other direction. So write the following in symbolic logic without changing their meanings. Be as concise as possible, or try to write it in as short a way as possible. If the phrases are statements, say whether they're true or false. If they're not statements, say so. So look at those, pause the video here, try those out, and we'll talk about them together. First one, for any real number x, x is non-negative if the absolute value of x equals x and conversely. So this right here, and if and conversely, is an if and only if. In other words, we can write it with that double arrow. So for any x in the real numbers, for any real number x, x is non-negative, x is greater than or equal to 0, and that's non-negative could include 0 as well, if and only if the absolute value of x is equal to x. And then that and conversely is taken care of already by the if and only if. Next, there is an integer n such that x to the n is equal to 1 for any real number x. There exists an n in the integers such that x to the n equals 1 for all x in the real numbers. Is that true? Yes, n equals 0 makes that work. X to the 0 is equal to 1 for all x in the real numbers. So this is true. The statement above was true as well. The absolute value of a number is equal to itself if and only if that number is non-negative. Next, at least one of the numbers x and y is rational. Again, at least one of is or. So x is an element of the rational numbers, or y is an element of the rational numbers. Let's see. Next, and this is not a statement. This is not a statement. It depends on the values of x and y. This is an open sentence. The product of any two natural numbers is a natural number. For any n and m in the natural numbers, the product of them, n times m, is an element of the natural numbers. Yes, that is true. And let's see, we could also write this as, so any universally quantified statement can also be written as an if-then statement or an implies statement. So n, m, element of the natural numbers implies n times m is an element of the natural numbers. We could also write it in that form. Next, there is an integer n such that n over 2 is an integer, but n over 4 is not. There exists some n in the integers such that n over 2 is in the integers, but, so that's also and, n over 4 is not an element of the integers. Now, is that a true statement? Yes. So for example, if we had like n equals 10, for example, then n over 2 is 5 is an element of the integers, but n over 4 is 2.5 is not an element of the integers. So this is true. Next, there is an integer x whose reciprocal is also an integer. There exists an x in the integers such that its reciprocal, 1 over x, is an element of the integers. Is that true? Is there some integer x that follows that? Yes. X is 1, and 1 over 1 is also 1, is in the integers. So this is true. Lastly, for any two rational numbers p and q, with p less than q, there is a rational number between them. For any p and q in the rational numbers such that p is less than q, there exists some r in the rational numbers such that p is less than r, which is less than q, such that r is in between those two values. That's one way we could write this, and yeah, this is true as well. We could see that by taking sort of the average of p and q.